How nukes are made. No math, no quantum mechanics. Nuclear fission is a naturally occurring phenomenon. Nuclear reactors are naturally occurring phenomena. 2 billion years ago, 16 separate reactors operated for thousands of years. They were fueled by uranium and produced plutonium just like modern reactors. Uranium and plutonium look a lot alike. It takes less plutonium to make a bomb, so uranium is generally used in reactors and plutonium is generally used in bombs. Looking at only one layer of plutonium atoms, it's easier to visualize the nucleus of an atom surrounded by its cloud of 94 electrons. Zooming in, we ignore the electrons and focus on the nucleus. Red particles are protons, there are 94. Dark particles are neutrons. Protons have a positive charge, and neutrons are neutral with no charge. Since positive charges repel each other, what holds the nucleus together and stops the protons from flying apart? A force called binding energy holds everything together. Nuclear fission releases some of the binding energy, and that release is where fission gets its explosive power. Fission usually happens when a neutron collides with plutonium's nucleus. The nucleus captures or absorbs the neutron, becoming unstable, and immediately splits apart into two new atoms. The fission fragments could be gold, iron, iodine, cesium, or silver, or almost anything. 3 neutrons also shoot out of the fission reaction, and when they collide with a plutonium nucleus, those nuclei also fission, producing more atoms and neutrons. The new atoms or fission fragments carry most of the tremendous heat. These atoms are also extremely radioactive. In most cases, they are responsible for the radiation and radioactive fallout. A nucleus is very distant from its electrons, empty like the space between Earth and Moon. If the nucleus were the size of a basketball, the space between the nucleus and the closest electron would be 2 miles. Plutonium is formed into a hollow sphere called a plutonium pit. The pit can be as small as a billiard ball. Then explosives are wrapped around the pit. Each multi-sided shape is called a lens. These are carefully designed to ensure the pit is crushed evenly and as fast as possible. The chemical explosion happens in 10 millionths of a second. The plutonium is compressed by a factor of 2 or nearly 3. The plutonium becomes supercritical, and temperatures reach several hundred million degrees almost instantly. Both plutonium and uranium are as dense as gold or twice as dense as steel. These two steel plates weigh 10 pounds together. If a plate were made of plutonium, just one plate would weigh 10 pounds. This little 3-pound weight would actually weigh 6 pounds, enough to create a significant nuclear explosion. Even with the explosives, fusing, and other necessary warhead parts, it would make an excellent terrorist weapon, a suitcase bomb. Humans didn't get smart enough to understand fission until 1938. Its discovery and subsequent use in reactors and bombs was inevitable. Fusion. Hydrogen is the simplest element in the universe. The nucleus contains only one proton, no neutrons, and has only one electron. Since fusion only involves the nucleus, we ignore the electron for now. Protons have a positive charge, so they repel each other. Forcing protons together in a fusion process is very, very difficult. Deuterium is a naturally occurring form of hydrogen. It has a neutron in the nucleus along with the proton. Neutrons have no charge, so the nucleus is still positively charged. Deuterium is easier to force into fusing, but storing liquid hydrogen at negative 423 degrees Fahrenheit is not practical for a bomb. Third form of hydrogen is tritium, which has a second neutron in the nucleus. Tritium and deuterium make excellent fusion fuels, but they still repel each other with their positive charges. The hundreds of millions of degrees from a nuclear explosion provides the heat needed. The pressure required is simply not possible with chemical explosives. Solving this problem is what made thermonuclear weapons possible. Lithium is a common element, the same one used in lithium-ion batteries. It has 3 protons, 3 neutrons, and 3 electrons. When a neutron is absorbed or captured, the lithium fissions. High-temperature helium, high-temperature tritium. The helium is very hot, raising the temperature of the reaction. Tritium is very valuable for fusion. Combining lithium and deuterium, we get a harmless salt, lithium deuteride. It's stable and not radioactive. When lithium fissions, there is a lot of free tritium and deuterium available. With tremendous amounts of heat and pressure, tritium is forced to fuse with the nearby deuterium. Out of that fusion comes a lot more heat, helium, and a very high-energy neutron. Binding energy is released since helium needs less than tritium and deuterium by themselves. Per pound, thermonuclear warheads are 60 times as powerful as fission warheads. Disassembled, we can see the weapon case of the B-61 bomb. Inside the aluminum weapon case, there is a radiation case made of very dense materials such as lead. Inside that is a plutonium pit with chemical explosives around it. Next is a shield made of very dense material. Behind the shield is a hollow plutonium rod surrounded by lithium deuteride fusion fuel. Surrounding the lithium fuel is another piece of very dense metal called a pusher tamper. The fission bomb explodes first, that's why it's called the primary. To simplify, we ignore the shield, the fireball, and half the radiation case. Now we are looking at the pusher tamper as it's being bathed in powerful X-rays from the primary. Looking at the atoms in the pusher tamper, I'll illustrate X-rays hitting a single atom. The superheated atom shoots off the layer of atoms at extremely high speed. For every action, there is an equal and opposite reaction. The reaction moves the entire layer inward toward the center of the pusher tamper. This is a little easier to understand, seeing all the atoms on the outer layer of the pusher go flying off together. The best analogy is rocket engine thrust. It's easy to see the massive amounts of brute force a rocket engine delivers when a very large payload is blasted upwards. The metal tamper becomes rocket fuel for crushing the tamper contents. That is why it's called a pusher.
When an average-sized star dies, the result is much less dramatic than a powerful supernova. Instead of exploding, it expands to become a red giant and then collapses. The material from the center of the star ends up squashed tightly down into a tiny, heavy ball called a white dwarf star.
Only 2 types of objects in the universe are denser than a white dwarf: neutron stars and black holes. The lithium fuel and the plutonium rod are crushed to the density of a white dwarf star. The rod has been compressed far more than the plutonium pit in the primary. This causes a fission explosion right in the middle of all the compressed lithium fuel. Several hundred million degrees of heat provides the temperature needed. The fusion fuel burns up in about 60 nanoseconds. A nanosecond is a billionth of a second, a timescale only a computer can do useful work in. Thermonuclear bombs can be expanded by putting a third stage into the bomb. The first thermonuclear explosion acts as the primary to the third stage. The third stage can act as a primary to a fourth stage, and so on. Of course, there is a race with time for each fireball created. America tested, manufactured, and deployed 3-stage thermonuclear bombs during the Cold War. As of 1987, the time race with the fireballs wasn't very successful. The fireballs blew up the fusion fuel before it was completely consumed, giving only a 12% efficiency. These are the 10 chapters in this video series. I will continue to release more videos and video series on this complex subject.